Have you ever stopped to think about what's really going on inside a jet engine as it screams down a runway? Or how a massive dam can power an entire city? Well, the answer to both is the same, and it's a class of machines that are pretty much the hidden workhorses of our world, turbomachines. They are absolutely everywhere, and today we're going to open up the engineer's toolkit and see exactly how they tick.
Okay, let's just jump right in. You've got the roar of a 747 taking off, and then you have the quiet, immense power coming from something like the Hoover Dam. These two things feel worlds apart, right? But they both rely on the exact same fundamental principle. It's all about moving a fluid, like air or water, to either inject energy into it or pull energy out of it. And that, right there, is the essential job of a turbomachine.
So here's the game plan. First, we'll get our heads around the big idea that splits all these machines into two main families. Then, we'll look at the specific jobs of pumps, and then the jobs of turbines. After that, and this is the fun part, we'll see how engineers play matchmaker to find the perfect machine for any task. And we'll wrap it all up with some really powerful, kind of universal rules that govern this entire field.
First up, the pump. Its whole mission in life is to add energy to a fluid. But here's the key thing to remember. The main goal is to increase the fluid's pressure. It's not always about making the fluid go faster. It's about building up enough oomph, enough pressure to overcome whatever is in its way, like trying to push water all the way up to the top floor of a skyscraper. That's a pressure problem.
And on the complete flip side, you have the turbine. So if a pump is an energy absorber, it takes energy and shoves it into a fluid. A turbine is an energy producer. It does the exact opposite. It pulls energy out of a moving fluid. As the fluid flows through, its pressure drops, and that energy that it gives up is what turns a shaft to do something useful, like spinning a generator to make electricity.
This lays it out perfectly. It really couldn't be simpler. For a pump, the energy of the fluid coming out is greater than the energy going in. For a turbine, it's the other way around. The fluid leaves with less energy than it started with because it gave some to the machine. One puts energy in, the other takes it out. That's the fundamental difference.
Okay, so let's dig into pumps a little deeper. Remember, their main gig is creating pressure. They're the muscle that moves fluids where we need them to go, whether that's pushing water through the pipes under a city or feeding fuel into a car's engine. Now, when the fluid we're moving is a gas, like air, engineers get a little more specific with their language. Is it a fan, a blower, or a compressor? It really just depends on the job. Think about it. A ceiling fan moves a ton of air, a high flow rate, but it barely changes the pressure in the room. A leaf blower? That gives you a bit more of a pressure kick. But a compressor, like for a jackhammer, that thing creates a huge pressure rise, even if the amount of air flowing through it isn't all that much. So how do engineers actually measure what a pump can do? They use a single, super important value called net head, often just written as H. It comes from a principle called Bernoulli's law, which basically just connects a fluid's pressure, its speed, and its height. So net head is really the total energy boost across all three of those things that the pump gives to the fluid. It's the key performance spec for any pump. But pumping liquids, well, it comes with a really nasty risk: cavitation. This is what happens if the pressure right at the pump's entrance drops so low that the liquid actually starts to boil, even if it's not hot. It forms these little vapor bubbles, and when those bubbles get swept into a higher pressure zone inside the pump, they collapse, and they collapse violently. It's like a series of tiny non-stop explosions that can literally chew away the metal parts of a pump from the inside out. It's incredibly destructive. So to stop this from happening, engineers have a very specific tool in their toolkit: net positive suction head, or NPSH for short. It's a critical safety margin. It's a calculation to make absolutely sure the pressure at the pump's inlet always stays safely above that boiling point pressure. Every pump manufacturer will tell you the NPSH it requires, and the engineer's job is to design a system that provides more than enough. All right, let's switch gears and head over to the other side of our toolkit, the turbines. So if pumps are all about creating pressure to get work done, turbines are all about capturing the power that's already in a pressurized, flowing fluid and turning it into mechanical work.
Dynamic turbines like these really come in two main flavors. You've got your impulse turbines, which work a lot like an old-fashioned water wheel. You have a high-speed jet of fluid that just smacks into a bucket and forces the wheel to turn. These are perfect for what we call high head situations, like a really tall dam. Then you have reaction turbines. They're totally different. They're fully submerged in the fluid and work more like an airplane wing, using pressure differences across the blades. These are built for situations with lower pressure but just massive amounts of flow.
A classic example of an impulse turbine is the Pelton wheel. It is such a clever and, honestly, pretty simple design. You have a nozzle that shoots a high-speed jet of water, almost like a fire hose, right at these specially shaped buckets on a wheel. Each bucket has this little ridge in the middle that splits the jet in two, turns it around almost 180 degrees, and in doing so, transfers almost all of the water's momentum to the wheel, making it spin like crazy.
And here's a great little piece of engineering lore for you. The story goes that the inventor, Lester Pelton, got the idea for that super efficient splitter on the bucket by watching how water sprayed off a cow's nose when it was drinking. I mean, inspiration really can come from anywhere, right?
Now, for reaction turbines, the absolute workhorse is the Francis turbine. This is the machine you'll find in most of the world's huge hydroelectric dams, like the Hoover Dam. Unlike the Pelton wheel, it operates completely full of water. The water gets guided through these complex, curved blades on a runner, and the pressure difference across those blades is what makes the whole thing spin. It's just designed to handle unimaginable volumes of water.
Okay, so we've got all these different kinds of pumps and turbines. This brings us to the real heart of the engineering challenge, which is how do you pick the absolute perfect machine for one specific job? It really all comes down to a kind of matchmaking process, matching what the machine can do to what the system needs.
And that's the million-dollar question, isn't it? You have a job to do. Let's say you need to move water from your basement up to a garden on your roof. You know the height difference, you know the size of the pipes. How do you choose a pump that's going to do that job well without being way too wimpy or way too powerful and wasteful?
Well, the first part of the puzzle is what we can call the pump's resume. Every pump comes with a performance curve that shows you what it's good at. It tells you how much net head or pressure it can produce at any given flow rate. You can see if you have zero flow, like the outlet valve is closed, it produces its maximum pressure, which is called the shutoff head. If you let it flow freely with no resistance, you get maximum flow, but zero pressure. And somewhere in the middle is that sweet spot, the best efficiency point, or BEP, where it works the best.
The second piece of the puzzle is the job description. This is the system curve. This has nothing to do with the pump itself. It's all about the pipes. It represents how much head the pump must generate just to lift the water up against gravity and to overcome all the friction from the pipes, the elbows, the valves, everything. And naturally, the faster you want to pump, the more friction there is, so the more head is required.
And the solution, the perfect match, is actually brilliantly simple. The pump will operate at the exact point where its resume meets the job description. It's the one and only flow rate where the head the pump can provide is exactly equal to the head the system requires. That's the operating point. And this whole matchmaking idea works for turbines too. You're just matching the turbine's power output to the energy that's available in the fluid.
Okay, to finish things off, let's do a little bonus round. We're going to look at a couple of rules of the game that are like engineering superpowers. They apply to pretty much all turbomachines, and they are incredibly useful. These are called the affinity laws, and they're basically a cheat code for turbomachinery. They let an engineer perfectly predict what happens if they just change a machine's speed. So if you double the speed of a pump, the flow rate doubles. Simple enough. The head or pressure it can produce goes up by the speed squared, so a factor of 4. And here's the kicker. The power it needs goes up by the speed cubed. That's a factor of 8. That's why even a small tweak in speed can have a huge impact on energy use. And the mnemonic makes it easy. Very hard problems. V for volume, H for head, P for power. As easy as 1, 2, 3.
And for our last rule, I want you to meet a very special number, the Betz limit. This number, just under 60%, is the absolute theoretical maximum efficiency of any wind turbine. Think of it as a cosmic speed limit for wind power. No matter how brilliant your design, no matter how perfect your blades, you can never, ever capture more than 59.26% of the kinetic energy in the wind. It's a hard limit set by the laws of physics itself.
So, from the pump in your dishwasher to the turbines in a jet engine, these powerful, elegant machines are everywhere, silently turning the laws of fluid dynamics into the energy that literally drives our modern civilization. They truly are engineering marvels, hiding in plain sight.
And it kind of makes you wonder, doesn't it? What other incredible engineering is right there in front of us, just waiting to be seen?